Good morning, everybody. Today we're going to go over the worksheet that I gave you guys yesterday while I was out. And I want to start out by saying that we are going to have a quiz on this on Monday. I know I told my B block class that we were going to do it on Tuesday, but I think everybody else kind of agreed that Monday would be a better day because there are a lot of other quizzes that are going to be going out on Tuesday, plus the fact that it's pep rally day. I don't want any more on your plates than it absolutely needs to be. So the quiz will look exactly like this. I will pick problems from this, change the numbers around, but here's how we do it, and I hope that you didn't have too many troubles on Friday with this. So looking at number one, care package being delivered to some college students at the University of Hawaii. The package is dropped from UPS plane flying above. Plane is 3,500 meters above the ground, traveling at 100 meters per second. This is a cliff problem, as it says over there. So we're going to start out by making our XY chart. I'm going to go VI, VF, A, T, D, as always with all of these. And we're going to take information that we know. And our VI in the X dimension is 100 meters per second. That means our VF is 100 because our A is 0. We don't know any of this other stuff, but we also, because it's a cliff problem, that's going to be 0, and that's going to be negative 10. We also know that the altitude of 3,500 meters, that's how far things can fall, so negative 3,500 meters. And if you recall, E equals BIT plus 1/2 AT squared. Let's start plugging some stuff in. We'll go with negative 3,500 equals 0 plus negative 5t squared. And this is all for the y. So if you look, it's only y stuff that's going to land in here because we're trying to figure out the time, which is the first thing we have to figure out in order to figure out v, which is the distance in the x. So we can do negative 3,500 equals negative 5t squared because that 0 just kind of disappears. And we'll end up with 700 equals t squared, and then we have to take the square root of 700 and end up with a time of 26.45 seconds. So we can plug that in here, 26.45, 26.45. And now we can use v equals d over t because remember this one only happens when the acceleration is 0. And hopefully you recognize that the acceleration is 0, so we can use this, which really just turns into distance equals velocity times time. And we know the velocity is 100. We know the time is 26.45. So the distance in the x will be 100 times 26.45, or 2,645 meters away. So that's where it'll land. That's how long it'll take to get there. So that's that, and that's that. Number 2, Empire State Building is 381 meters tall. If I was to throw a penny off of it with an initial velocity of 9 meters per second, how far away in the x direction would it land? How long would it take to get there? And ignore air resistance. So once again, we're going to make our little chart. And what I'm going to do, I'm going to be intelligent here. I'm going to make a really nice one. Why do you always do this? VI, VF, A, T, D. There's my x. There's my y. And what I'm really going to do, sorry for making the video a little longer than it really could be. However, we'll see why hopefully soon. Boom. Yes, cool. So now I can just paste my one chart into the next, all of the other things. So let's keep going with this. Sorry about that. We're going to throw something off with initial velocity in the x dimension of 9. And it'll have a final velocity of 9. The acceleration is 0, negative 10, because it's a cliff problem, essentially. We're throwing something. There's the Empire State Building. We're throwing it off like that. So the y initial velocity is 0. Continuing on here, if there's anything else we know, it's going to fall 381 meters. So negative 381. How far away in the x direction will it land? How long will it take to get there? We have to do this first to figure out that. So we'll do the time first and then the displacement second. Let's go with d equals bit plus 1/2 at squared. Our displacement in the y dimension is negative 381 equals our initial velocity was 0 times anything's going to be 0 plus 1/2 times negative 10, negative 5 t squared. Simplifying this, we will end up with t squared equaling 76.2, and then the square root of both of those will give us the time of 8.72 seconds. Now what we can do is plug this into displacement in the x. Figure that out. Again, we have an acceleration of 0. D equals velocity times time in the x, which is really, again, the way we get that is velocity is distance over time, and we just rearrange this equation to give us that. So our displacement will be 9 meters per second times the 8.72 seconds it went for, and that will give us a displacement of 78.3 meters away. So there's your time, there's your displacement. Marble is rolled off the table, blah, blah, blee, blee, blah. Let us move this down just to move it all just a little bit down. Good. Marble is rolled off the table by taking 1 second to travel 0.9 meters, then it rolls off the table. The marble lands on the floor 1.2 meters away. How long is the table? This should sound familiar. You did a lab very much like this. You were graded on it. It's where you drew on the floor. It was very fun. Only this time I'm not asking where to put the x. I'm actually asking you to use where the x was to figure out the height of the table. It's actually very similar to the Wile E. Coyote problem, but it wasn't Wile E. Coyote problem. But it was something landed this far away from a cliff. How high is the cliff? So we know to start this is a cliff problem, so that's going to be 0, that's going to be 0, and that's going to be negative 10. Now we can look at the other stuff. The marble is rolled off the table by taking 1 second to travel 0.9 meters. We remember we need the x velocity, so we actually need, here's your table, we need the velocity as the marble rolls off. And we kind of assumed when we were doing this whole lab that this velocity would be constant, which means we could use the d equals velocity times time piece. We know it took 0.9 meters and it went some velocity for 1 second. And if we divide both sides by 1 second, 0.9 over 1 is 0.9 equals my velocity. So actually this is where we're going to get that one from, 0.9 meters per second. So that was the first thing you have to do. You have to figure out first how fast that marble is going as it leaves the table. And it is going, it is a cliff problem, so that's going to be 0. So the rest of this is kind of not useful anymore. But now we have this. So it's 0.9 meters per second. That's how fast it's going as it rolls off the table. I want that. I want. Oh, how I love Smartboard software. 0.9 meters per second. All right. So if we got that 0.9, we know that's going to be 0.9 because we're traveling the x dimension. We don't know the y. However, we do know the x, and the x is 1.2. So here's our table. It went off at 0.9 meters per second. It lands 1.2 meters away. So now we have to figure out that height, that distance. Fair deal? So how do we do it? Well, we don't have the information here to get our time, but we do have information here to get our time. So let's try and use this information here to get our time, and then we can plug stuff back into the velocity or distance or some other formula and figure out if we can get the displacement. Starting there, we know velocity equals distance over time because we're dealing with something that has an acceleration of 0. We know the velocity is 0.9 meters per second. equals our displacement 1.2 over our time, which we don't know. So we know the marble was going 0.9 meters per second and it landed 1.2 meters away, but we need to figure out the time. We can put this over 1, and then we can do some cross multiplying. 0.9t equals 1.2, and divide both sides by 0.9, or g, 0.9. We should end up with a time of 1.3 seconds. So I hope you got something similar. 1.3. Now that we have that, we can backtrack and figure out and if you need stuff, pause, and then you can go back and write stuff down and hit play again. But now that we've got the time, we can figure out how far it fell in 1.3 seconds, and you're going to see this is going to be a very tall table. Distance equals VIT, distance in the y, that is, plus 1/2 AT squared. VIT is going to be 0 plus -5, 1.3 squared. D in the y is going to be, what's 1.3 squared? It's actually 5 times 1.69. Then you can multiply 1.69 times -5, and you should get -8.45 meters. 35 words or less, the marble falls 8.45 meters. That's why we got that negative there. So the table is 8.45 meters tall. Hope these first three helped you out. Next up, we can go ahead and play with real two-dimensional projectile problems. As always, I'm going to make my chart, VIVF ATD, before I even get started with this, and we can start plugging some stuff in. During Swan Lake, a ballerina jumps into a pirouette at an angle of 39 degrees and an initial velocity of 3 meters per second. How much time does she spend in the air? How far away does she land? And I'm always going to ask you how much time they spend in the air, because you need that to get the distance. And if you also remember, anytime I give you an angle for dealing with a launching problem, and you use the velocity as a hypotenuse, and then you got to figure out where we're going with the angle. So you got a 39-degree angle. I made a nice, more or less, a triangle. If you remember your trig, again, I'm hoping you remember this. The way to get this and this is using SOHCAHTOA, and simplified, it'll end up with being 3 cosine of 39. And this will be 3 sine of 39. And this 3 becomes irrelevant to us because now we're going to have an initial velocity in the x dimension and an initial velocity in the y dimension. And doing that, plugging into your calculator, you should get 2.3 meters per second in the x and 1.88 meters per second in the y. So now, this stuff, forget about that, can be thrown in here. Our initial velocity in the x again was 2.3. Final is going to be 2.3. Our acceleration is going to be 0. And the y is going to be 1.88. And our acceleration is going to be -10. Now I want to know how much time we spend in the air. If she goes up with 1.88, she's also going to come back down with 1.88. So we're going to say -1.88 is her final velocity. And that's actually not entirely accurate because we're going straight up and then straight down with 1.88. So that's that. That's our velocities. We need to figure out the time now. And the easiest equation I can think of, if you have an initial and a final velocity and an acceleration to figure out time, is going to be VF equals VI plus AT. -1.88 equals 1.88 plus -10 times time. We have to subtract 1.88 from both sides. So we should get 0 plus -10t on this side of the equal sign. But -1.8 minus 1.88 should actually give you -3.77. And simplify this out. I can actually get rid of that little 0. So you really just have -3.77 equals -10t. So now you can divide both sides by -10. You should end up with, can't drag that. I'm just running out of room. You should end up with the negatives canceling out. 3.77 divided by 10 is 0.377 seconds equals time. So that's 0.377, which means x is going to be 0.377. So there's your time. Second part of this is how far away does she land? I'm going to get rid of this too to give myself some real estate. How far away does she land? Well, we know the distance, we're looking for distance in the x, equals vit plus 1/2 at squared, but the a is 0, so all we really need is d equals vit. D equals 2.3 in the x times 0.377 seconds, and you should end up with your displacement being 0.86 meters. So your time is 0.377. Your distance is 0.86. We should use basically the same procedure on the next problem, which is the David Beckham problem. Again, I'm just going to drag. Maybe I should have just kept right making the charts. All right. So David Beckham can kick a soccer ball. Blah blah. I give you an angle and a velocity. Once again, I don't want purple. Looking against purple. Just don't like looking at it. So I guess it's a lot against purple. We can kick it 25 meters per second at an angle of 44 degrees above the horizon. So once again, we've got a triangle. This is the real velocity that he kicks it, but it's going somewhat in the x and somewhat in the y. We need to figure that out. So to do the shortcut again, 25 cosine 44 and 25 sine of 44. This should give you 17.98. This should give you 17.36. And a good way to check it is you think to yourself, well, geez, this is 44 degrees. It's pretty close to 45 degrees. And if it's a 45, 45, 90 triangle, this side should be the same as this side. 17.98 is pretty close to 17.36, so we're in the right ballpark. If you ended up with 17.98 here and 2 over here, or vice versa, you'd know you did some algebra wrong. But at this point, we can take this triangle and break it into the x and the y. So the x initial velocity is 17.98, and the y is 17.36. And now I don't need this anymore. So I'm actually just going to erase it to give myself some space to do some other writing. The final velocities here, because I'm an advocate of filling in as much of this as we can and then figuring out what we need afterwards. Final velocity in the x is going to be the same because the acceleration is 0. But this is going to be negative 10 as always. And if we were going up 17.36 meters per second, the ball is going to come back down 17.36 meters per second. So we're going to put a negative 17.36 meters per second there. Erase this. If he kicks at an angle of 44 degrees, how far can it go? How long does it stay up in the air? I don't know how far it can go in the x. I guess that's what I want ultimately. But in order to get this, I need a time. I can't really do it with the x stuff, but I can definitely do it with the y. EF equals VI plus AT. If you do this with your x stuff, you're just going to get a time of infinity or time of 0. So it can be any answer because you'll end up with 17.98. You get 0 equals 0 times t. So anytime you put, you'll get 0, and it'll work algebraically, but it's not very useful information. Always use your y for this equation to give you the time. So negative 17.36 equals 17.36 plus negative 10 times t, which I don't know. Again, we're going to subtract 17.36 from both sides. And we'll have 0 plus negative 10t on that side. We'll actually have negative 34.8 1.72 on that side. And now all we have to do is, that's nonsense there, so divide both sides by -10. Again, we were multiplying by -10 here, so we divide it. We were adding 17.36 here, so we subtract. That's the algebra again. So we should end up with a time of positive 3.472 seconds. 3.472, 3.472. So now we can figure out, I got a t, I got a velocity. Remember, distance equals velocity times time. D equals 17.98 times 3.472. You should end up with a displacement of exactly 62-ish meters, which is a little more than half a football field, or a soccer. Football, soccer, half a soccer field. So I hope that helps. Again, anytime we're giving you the angle and the velocity, you use that velocity as your hypotenuse, and then you can figure out your x and your y. Alright, so then the x and the y go up in here. Number 6, we're almost there. It's almost done, and hopefully this isn't too long and boring on a Saturday or Sunday for you. Let's start out with Superman. I love this problem. I love Superman, but I like this problem anyway. Said that Superman can leap tall buildings in a single pound. Can Superman leap over the new Freedom Tower in New York City if the tower is 1,776 feet, which doesn't do us any good because we don't know anything about feet, but I also tell you it's 647 meters tall. Assume Superman can jump with an initial velocity of 116 meters per second. So that's really important that we have that initial velocity. 116 at an angle of 80 degrees to the horizontal. So now we have to make our triangle, and we're going to somehow get the x and the y, which again are going to go over here. And to get the x, it's going to be 116 cosine 80. So this should actually be very, very, very small. And 116 sine 80. This should be very, very big. And if you do it out, you should end up with 20 meters per second on that side and 114.23 meters per second on the y. So we can plug that in. 20, 20, 0, -10, -114. We'll get into that in a second, and positive 114. All right. So he jumps up with 114, and that means he's going to go up. Here's the tower. He goes up, clears the tower, comes back down, and he's going to land in the y dimension with the same 114 meters per second. Remember in class, if we had different levels, he would land at a different speed that he took off with, and then there's a whole other algebraic calculation. But I'm trying to keep this relatively simple. We're keeping everybody on the same height here, so he's going to go up from the same height, so he'll hit the ground with the same velocity with which he left. So now that my triangle is done, I don't need it anymore. Go by. We can start actually playing with this. Please tell me exactly how high Superman can jump. Does he clear the tower? Okay. I'm not going to put this 647 here. And the reason is I want to see how high he can jump. So let's solve for that, and then we can compare it back to the 647. Let's see. I have a feeling this is actually going to be pretty close. The cool thing is I don't need any of this, and this being the X stuff. The reason I don't need any of this is because it really is just a one-dimensional problem. Can he jump as high as the building? So let's see. D equals BIT plus 1/2 AT squared. I can figure out time and then plug it in here, but you know what? I'm not gonna. This is another equation that I can use, especially, honestly, only because I can use VF squared equals VI squared plus 2AB because I care about the displacement in the Y, not the X. So VF squared equals VI squared plus 2AB. Negative 114 equals 114 squared plus 2AB. These are going to give me some really big numbers. But I did it, and I'm going to subtract everybody, so I'm just going to simplify this out. You're going to end up with, oh geez, I'm just kidding. VF is 0. I'm wondering if it actually wasn't as big of a number as I thought it was going to be. So 0 squared equals 114 squared plus 280. And 114 squared is actually 12996 plus 2 times negative 10 times d. So how do I get rid of this? Well, if I'm adding it to this stuff and I want to isolate the d, I got to subtract it from both sides. Minus 12996. So negative 12996 equals 0 plus negative 20d. What I'm going to do is erase that negative 2 or 0. Just kidding. I'm going to erase the 0. Now I can divide by the negative 20. So that'll leave me with a d by itself. The negative 20s cancel out. I should end up with a displacement of 649.8 meters. So positive 649.8. How tall was the new tower? 647. So he can jump almost 2 meters, actually almost 3 meters taller than the tower, which the spire actually counts as part of the height. So if you've actually seen the building, it's really, really tall, and it's got a spire on it, so you can make it all the way over. So I hope that helped. Sorry, I got a little I got confused in here. I just confused myself. Hope I didn't confuse you too much. 7. Potato gun launches, and this is actually something that I usually like to do with the potato cannon, but we didn't really have the opportunity to do it this week, and we're probably going to be moving on next week, so I'm sorry to say it. If we have time in the spring, we'll go back out with the potato cannon as part of the review. But, long story short, we used the time up and down to figure out the initial velocity here, to play here with where it's going to land. So I'm actually going to just leave this as a one-dimensional kinematic problem for starters. VF, ATD. During our potato launches, one hang time was exactly 12 seconds when shot straight up. Please use the data to find the initial velocity. And again, it's one-dimensional because we're only going up and down. We're not shooting at an angle. So there is no theta. The VI is what we're looking for. The VF at the top, though, at its highest is 0. And if the hang time was 12 seconds, the time to get that high is 6 seconds. Okay, so we're really dealing with a VI equals VF plus AT scenario here. I'm just kidding. It's VF equals VI plus AT. The VF is 0. The VI is I don't know what, plus the acceleration is negative 10 times t, which is 6. So 10 times 6 is going to be 60 with the negative. VI equals negative 60 equals 0. So we got to solve for VI, which means we have to add 60 to both sides. 60 plus 0 is 60 equals VI. And the cool part is it was negative 60 over here, but we have to add 60 to both sides, so we end up with a positive 60, which means that the potato cannon launches with a velocity of 60 meters per second. So now, using that same velocity, please predict where it'll land if we shoot it at 45 degrees. I'm going to start out with the XY chart. And now, you can really start thinking about this. So we said before, the velocity was 60. We're going to shoot it at an angle of 45 degrees. Those of you who put 60 here or here, especially here, shouldn't have done that, because we're not shooting it straight up anymore. So now it's not going to go all 60 meters per second straight up. It's going to be split into some X and some Y. So, one more time, this is going to be 60 sine 45. This is going to be 60 cosine 45. And at this point, we should remember that it's a 45, 45, 90 triangle. So if I get this side, I have this side, or that side, I get this side. Regardless, both sides are 42.2 meters per second. So I can put 42.2 here and 42.2 there. I don't need this triangle anymore. All right. Again, the x, we don't speed up or slow down. 42.2, 0, this is negative 10. It will land with a negative 42.2. And the difference between this and the first one is this I'm concerned about what's the displacement from start to finish, from here to here. With this first little piece, I was only concerned with the displacement from here to here. So I'm looking for the displacement from when it was going fast to when it was at rest. That's why we use the VF of 0 there. Here, I want to know from when it's got a VI of 42.2 going up here to when it's coming back down with negative 42.2. We're looking for that whole time. So that's why you see the opposite velocities here and the 0 for the final velocity here. We're looking at different points in time for the particular projectile. Come back down. Alright, so let's erase this. So now we got to figure out, we want to know where it's going to land. But to do that, we need the time. As much as I would like to say VF squared equals VI squared plus 2AD, we'll just get 0 equals 0 times the displacement, so you get everything. So we really have to figure out the time here. And again, we'll use time in the y. VF equals VI plus AT. Negative 42.2 equals 42.2 plus negative 10t. And that would actually allow you to subtract 42.2 from both sides. You should end up with a negative 84.4 equals negative 10t. Divide both sides by negative 10, because these are multiplied, so we're going to divide it. You should end up with a time of 8.44 seconds. Now that we have that, erase. Now I can go back to d equals VIT plus 1/2 AT squared. But again, remember, we're in the x dimension, so the a is 0, which means this all turns to 0. So we're stuck with this equation you read about. D equals VIT. D equals 42.2 in the x times 8.44 seconds in the x. And you should end up with a distance of 359 meters away, which is 3 football fields. And again, this is ignoring air resistance. We're living in happy physics land. So if we did it in real life, it would definitely not land that far away. But if there was no air resistance, it would. So I hope this helped. Study up. I will see you on Monday. One piece of advice, you definitely probably going to want to review the chapter. I'm going to throw a couple of multiple choicey problems. I said, prove to me you read it. Most of you read it. Some of you didn't. We'll see how you do on the quiz. But again, expect to see some of these and expect to see some multiple choice on the quiz relating to the reading. Alrighty? Can't wait to see you on Monday. Bye-bye.